All right, I think we can get started. Essie, do you want to introduce the club and then I can do the rest?
Yeah, so sure. We are Society of Physics students at the University of Massachusetts, Boston. We just like we do physics stuff. So we have like a bunch of people who come in for lectures once in a while. So we actually did an intro to printing and design earlier this semester, which was really cool. We had a a presentation about the Coast Guard, which is really cool. Yeah, just like a bunch of stuff like that. And yeah, so that's what we do.
And today we'll be going over how to 3D print stuff, super basics. So if you have no idea how 3D printers work or any idea how 3D designing works, we'll get you started on that. My name is Gianluca. I've been at UMass Boston for 4 years now. I'm an engineering physics major, and I'm representing the physics department under this. So I also work at the Makerspace, like I said, and what we do at the Makerspace is 3D print stuff for students. And my exact title is Mom. I'm the maintenance oversight manager, which means I make sure that all the printers are always running smoothly, and I always report to the higher ups when things need to be fixed, if we need to purchase anything to fix the printers, and just general maintenance. But we're all a team. We all do everything together. So let's get started. So today we'll be going over how do you make things. So in general, like general fabrication, not just 3D printers. We're going to go over the specifics of FDM 3D printers. FDM stands for fused deposition modeling, which is also, you can think of deposition as depositing. So it's placing filament. And we'll be also going over the basics of 3D design, techniques, things you want to go for. And eventually we'll even attempt to make your own, or I'm going to show you how to do one and you can follow along if you'd like. So specifically, how do you make products first? So there are different types of manufacturing ways. There's one of the more machine type ones, and that's subtractive manufacturing. But subtractive manufacturing isn't just machine type. You can also think of it as carving or sculpting. So what's carving or sculpting? Give me a second for the video to load. There we go. So in order to make something through sculpting or carving, what you have to do is remove material from something. So you can see here's a block of wood. And in order to create a final product out of it, you have to remove the wood from the outside and work inwards. And like most manufacturing techniques, if you mess up, you have to restart, or you can recycle material. For wood, it's not that easy. And we're not going to count adding material, but you can see how you have to remove the material in order to get a structure underneath. A more automatic way of doing this would be machining. Now, machining is very similar, except it's done through an automated process that is, coded ahead of time. It can be done manually, but for specific things, most of the time, especially on large scale pieces, for instance, wheel hubs, aluminum wheel hubs, they're actually machined through an automated process that's been predetermined. So you have a 3D model, you put it into the software, and it turns that 3D model into the machine code, and the machine actually uses a spinning drill bit that cuts out material. So you can see like here, it's cutting out material. It's completely automated at this point. You have to still watch it because the machine doesn't know what it's doing. So you have to make sure it doesn't mess up or destroy itself, because it doesn't have safety features for the most part. Some more advanced machines do, but smaller machines that you can get at home, for instance, 3D printers, don't. In terms of 3D printers, there's additive manufacturing. Now, additive manufacturing is adding material instead of removing material. But instead of 3D printers, a lot more common way of adding material or creating something from an object that you need to fill in is actually injection molding, not just 3D printing. So I'm just going to show this video of how injection molding works.
Many everyday objects made of plastic, such as PET bottles, toothbrushes, spoons, screw cap closures, and cups, are manufactured using the injection molding process. But how does this actually work? The raw material is plastic granulates. This is fed into the machine. Then it's melted in the plasticizing unit. The screw conveys the molten material into the screw antechamber. When sufficient molten material is available, the melt is injected into the mold, which is installed in the machine's clamping unit. After a short cooling phase, the clamping unit finally opens and ejects the finished plastic product. And then the process starts over.
So you can see a raw material, for instance, these plastic pellets are melted.
Into the machine.
Melted, they're pushed through an auger, heated, into a liquid form. So they're going from solid to liquid. They're pushed into a mold and then solidified again. And that's how these objects are created. Now, something that works very similarly, which is you can think of a 3D printer as a hot glue gun. What does a hot glue gun do? It's the same exact thing. It takes a solid piece of glue, heats it up, liquidizes it, and then deposits it onto a surface, and then it cools again and becomes solid. And now for glue, that's for attaching things together. So you can see on the inside, it's a stick of hot glue, but it's solid, cold, heated up in the chamber, turns into a liquid, and it's pressed out. Now, how does 3D printers do it? It's very similar. So instead of hot glue, you have filament spools. Now these filament spools can be of different materials. We'll get to that later. They go through a hot end, and you can see this is the hot end here. It has a cooling piece to keep the rest of it cold because this gets really hot. And it melts it inside of here, and then it deposits it layer by layer. So you can see here, there's a heating element on the inside of here. That's just a simple drawing. There's actually an extruder motor that will push the filament through the hot end, and then it will cool as it comes out. Now, what does that look like if you get really close up? It looks a little bit like this. So you can see it's not doing the entire thing like in injection molding. It's actually doing it small part layer by layer. So you can see it's actually drawing out a material or drawing out a shape. And this is automated just like the machining process, and it's removed where it was removed. In this case, it's added. You can see it's actually doing a predetermined thing. You give a software a model, it will take that model and turn it into the machine code where it tells it to go to this position, goes to this position, goes to this position, extrude this much amount, extrude this. And that's all these files are, is just big lines of coordinates basically. And you can see it's able to draw out these shapes. And if I were to skip ahead a little bit, you can see how it starts drawing on top of each other. And in order to fill in large areas, it actually has to overlap itself, or even for hollow areas, actually draw a structure on the inside. You can see just there is actually it's not completely solid. It's a structure on the inside that's called infill. We'll get to that later as well. And then in the end, you get the final product, and it looks a little bit something like that. It's a little boat. It's called Benchy. It's a very popular thing in the 3D printing world because it's a torture chest, basically. There's a lot of material. I'm not going to get into that much, but there's a lot of features on that print that make it hard to print for printers, and you can diagnose problems with the printer with that. So with that said, let's go into the specifics of 3D printing. So there are overhangs and supports. There's adhesion to the build plate. There's orientation. And then, like I said before, there's layer height and infill. And there's color and materials. So we'll get to materials and colors last. But first, we'll go to overhangs. So printers can't print midair. They have to print on a surface. So what happens when they print midair is, while it solidifies kind of right as it comes out, it takes a minute for it to cool down and become solid. And you can see here, as it extrudes out, it's solidifying, but not right away. So it doesn't look like a perfect line of plastic coming out. You can see how it's getting hard over here, but it's still liquid. The person just pull it off with their fingers. It's not that hot. But yeah, you can't print directly in midair. So how would you print something like this, for example? Well, if we tried to print that, we get this. Right? We have the model. We have it in the 3D editor, whatever they're using. And now they put it into the printer, and it's printed the legs okay. But now it's getting to the arms, and there's nothing underneath the arms to support it. So it tries to solidify it, and you can see it starts drooping and then solidifies. So it's not a perfect process, but machine doesn't know what it's doing. It's just executing those XYZ coordinates that I said before. And eventually, there's enough of that material underneath that it's able to support the rest of the arms. So the top looks okay. However, the bottom is all stringy and wiggly, and that's no good. So how do you fix that? Well, you use support. Now, what is support? Support is a part of the print that the machine, when you take the model and put it into the software to make it into the machine code, that software will actually make these sacrificial or removable and then throw them away parts that allow you to print midair. But it's not midair anymore, right? You're printing on top of these supports. So you can see in the far left picture, it was no support. So the belly right underneath started sagging and stringing down. And then eventually it started building on top of those strings. And then the top was okay. You can see the tail in the far right picture actually isn't attached to the ground. So on the far left one, it started printing midair and completely failed on the tail for the most part until it got close enough to the legs where it had something to print on top of. In the middle picture, however, the support was added. And now this was before removing it. So this was directly off the printer right as it finished. And that's what it looked like in the editor. So you take the model, you put it in, and it builds these supports underneath the structure where it needs the help, where it needs to print midair. And after that's done, you take it off the printer and then you remove those support materials. And even the raft underneath, you can see by the pads of the feet, there's a raft. That's for build plate adhesion, which we'll get to in just a second. But after that, all that stuff is removed, you end up with the right picture. And that's the final product that you'd give to someone or you'd finish and you'd put it up on your shelf or something. Yeah, so in terms of the support, so you can see there's pads underneath the feet. There's build plate adhesion. Now, build plate adhesion is really important for printers. The printer doesn't know what it's doing. So it just goes to this coordinate, extrudes filament, goes to this coordinate, extrudes filament, right? But what happens if the big part that you're printing on top of moves? The printer doesn't know that. So what happens is you get something that looks like this. Now, what is this? This is what's known in the 3D printing world as spaghetti. Can you guess why? Right? So the problem is when the filament comes off, it starts printing midair and there's nothing underneath it. It just keeps extruding. So it tries to finish the model, but there's no model underneath the printer head. So it just keeps putting filament out, filament out, filament out. And it's just a big mess and it's terrible. Sometimes if it's super bad, what happens is it will ball up on top of the hot end. And you have to heat up the hot end and actually pry it off. This one isn't too bad. You can see how I don't know if you can see my mouse, but up here, there's not too much filament. Most of it's come down here. At the very top where there's a black on the two metal rods, right in the middle there, there's some red. There is a little bit of plastic there. What would happen is if that plastic were not stringy and if it was just kept extruding, it would turn into a big ball of plastic. They're blobs of plastic. They're not just strings anymore. It's not spaghetti. So yeah, that's one important thing about printing. Another important thing other than build plate adhesion is orientation. Now, in terms of orientation, it's really important to get a model in a certain direction. So this is an example of a 2-color print. So instead of having that one hot end in one extruder, it has 2 separate ones that are next to each other. And it will actually offset them to switch color, print with like this one, and then offset to my other finger, and then print with that one. And it has 2 separate colors in each one. And you can see here how they are in 2 different orientations, right? So one cone is on its side and one cone is upright like you'd normally see it. Now you can see on the right one, there's no supports, but on the left picture, there are supports. Well, why is that? So on the left one, it has to print midair here, right? Because if they weren't these structures underneath the purple and green parts or red and green parts, anyway, it would just be printing midair and it would fail on the underside of the print. So what happens if you were able to rotate it in order so that there's no parts that are steep overhangs, like a cliff, or almost not a cliff, but like a bridge, it won't need those supports because there's nothing that's printing midair. It's able to print on top of itself. And something, for an example, would be like this spaceship. So what's happening here is it's in 2 different orientations in the software that takes that 3D model and turns it into the machine code. In the middle picture, it's taken that model and turned it into the machine, and it's rendering an example of what it would look like. And then on the right one, you can see it's also in different colors based on the type of line. So there's an outside line, there's a top line, and they're just 2 different colors. However, when you look closer, you can see the surface quality as well. So orientation isn't just to help you with support, it also helps a lot with the quality of the picture. So you can see on the left one, right, it has to do those layers on top of each other. So you can think of it like a map where it has like those rings around mountains, the height maps. If you have really big layer heights, it's going to look really bad on the left one. However, if you use the right one, right, they're a lot finer detail and there's not as much bumpiness there going on, where it mostly smooths out when you actually print it. It looks a little bit jagged in the picture, but you're not getting that step layer feeling in the right one, unlike the left one. Now, in terms of the steps, there's also layer heights. So layer height is the thickness of each layer that the printer places down. And you can see it goes from 0.1 to point. You can set it actually to anything, but it's limited by your printer. But normally the 0.2, 0.15, 0.25, that was a weird noise, is normally around the limit of where you want to print layer heights. And then what it looks like is like this. So you can see on the right picture, the very far right picture, those are really big layer heights so that you can see there's not a lot of detail. This would also print a lot quicker. So it's good if you just want to prototype something. But if you want more detail and more strength in general, you want to go to the more smaller scale layer heights so that you get more detail within each layer. Now, this also means it takes longer because you have to do more layers, but it looks a lot better, and it can even be stronger because it actually squishes the layers together and melts when it melts, so it helps them adhere together a little bit better. Now, we were talking before about infill, and you can see here's a picture of Einstein. There's a 3D model of his head that's been printed, but on the inside, this was stopped mid-print. The inside isn't solid like you would think, right? There's that infill pattern. It's not solid on the inside. There's a structure on the inside, right? So what is that structure? That structure is infill. Now you can change the pattern based on whatever software you're using to turn that model into you turn that model into the 3D structure and the code, whatever, for the machine. You can change all the settings for the infill. You can change, for example, on the left, these are all the same density, so how compact they are, but each one is a different design or different, it's a different type of infill. So you can see on the top left, you get Hilbert, and on the bottom right, we get line and grid and, honey and 3D honey, and they're just different strengths to them. So some of them, there are more that you can't see that aren't in this picture, but each one you could just stop it. You could not even print out the outside. You could just print out this, and sometimes that will look cool. And then on the right picture, there's the actual density. So on the top right is the 100% filled inside picture. That's a lot of plastic. However, if you were to go to, I'd say 40 or 50%, you'd get about the same strength as 100%. You don't need all that structure on the inside, especially with how thick the plastic can be sometimes. So that's a really easy way to save plastic. And if you're not going to be handling the print a lot, if you're going to leave it on your shelf as decoration or something, you might even go to 10 or 20, right? 10, 15, something like that, because it's not like it's going to be man-held. It's not going to be thrown on the ground all the time. So it's not like it has to be super strong. You have that outside layer that's pretty thick. I remember from before that picture of Einstein, you can see how thick his head is compared to the inside layer, which are really thin lines on that grid. So that structure gives a lot of support on the outside, and then the inside doesn't need a lot sometimes. So yeah, that's infill. Now, I was talking last about color, right? So there are different colors that you can print stuff in. Now there's 2D, there's 2-color, 3D color, whatever. Most printers that you're going to see on the market, especially hobby ones that you guys could purchase and buy at home, are single color filaments, single color printers without modifying them. That is, there's a big community around 3D printers and how to modify them and how to experiment with them, how to change what they do, XYZ, how to completely replace parts of them with other custom parts. For example, this is most likely PLA. PLA is polylactic acid. It's a corn-based filament, and they dye it to become in specific colors. Honey's pretty cool. There's actually more. I can show you guys later. There's actually, in the slicer that I use, there's some different ones that I didn't show you. There's one called Gyroid, which is really fun to watch. If you like look through the print, I'll show you that later. But yeah, these different colors, normally they're all single color. There's also some exotic prints like gold or metallic colors. But there's also some specialty materials, which I'll get to in just a minute. But there's also not just the single color ones, there's dual color, right? So if you have those two extruders, you're able to print in two different colors at once. As an example of this, a printer, instead of having that one nozzle attached to the arm, you'd have two nozzles with two different motors and two different spools of plastic attached to it, which allows you to print in two different colors. Now, another way to color something would be just to paint it. Now, if you want something really complex and not a lot of money, you'd want to probably do something like this, right? So you just print in the one color, you get a nice cheap printer that's able to print in decent quality. You can sand it down if you want, because it's just plastic. It sands down really nice. And then you're able to print it afterwards. And you're able to, you're able to paint it afterwards. But you're not limited to just the colors of plastic that you have for the printer, right? If you use paint, you can just buy any paint color you want and mix them together to get different colors. You can see a lot of detail in this group picture on the right. So now there's specialty types of filaments. So these are PLA for the most part. So PLA, polylactic acid. There's also PETG, which is polyethylene tetraethyl, I can't say that, glycerol, and then ABS, which is acetyl butadiene styrene, right? So those are special types of plastics. Those I don't believe are biodegradable. I believe PLA is biodegradable. It takes a while. It's not like a year. It doesn't just degrade by itself. So you can leave it on your shelf and it'll be there for a while, but it is a naturally based plastic. However, there's some special materials. So I'm going to open up the chat to you guys. I want you to guess, what is this? What do you think material this is? Just want at least 3 people to say it. All right. Yeah, so this is concrete. So you can see, for example, you are able to print in concrete. Now, how does concrete work? You go from that solid or even the mushy solid, right, to a mushy liquid. So we go normally in 3D printers, you go from liquid to solid or solid to liquid to solid. But in this case, we're going from either a mush liquid to a solid afterwards, right? So you can do even like soft materials with that. So you can see these people are able to extrude concrete out of a big machine and then able to paint it afterwards and turn it into a house. And now this was made for, like I said, just under $10,000. And this is the machine that they use that's able to extrude concrete, right? That's pretty cool. Now, I mean, I think even NASA is thinking about testing 3D printers like on the moon or on Mars or something. I can't tell you yes or no that they're doing that, but I've seen word of it online that they're trying to actually take the moon dust and mix it with like a concrete, like a binder, in order to be able to 3D print with it, which would be cool. Another material that I want to show you guys is, I'm going to show you the picture for it. What do you think that is? So it looks like plastic, but it also looks brown. What do you think that is? I just want one guess.
Wood?
Wood?
Wood.
Yeah, you got it. So that's wood. So what happens with these wood filaments when you sand it, do you think? Do you think it smells like plastic? Or do you think it smells like wood?
I think it smells like wood.
Yeah. So what happens is these plastic actually has particles of wood in it. So it's Christian, I could be wrong, but I think it's what, 30%, 50% wood particles? I don't remember.
Last time I checked, it's like 30-40%.
30-40. Okay, so you can see how much wood there's actually in this filaments. So even if you sand it down, it looks exactly like wood. It smells like wood, and it sands like wood too. So you can see how there's somewhat of a rough texture to this elephant. You could actually take a piece of sandpaper, and even for the plastic ones too, you could take sandpaper and actually sand it down smooth again. And I got one more material for you guys. What do you think that is?
I think it's like organic material, maybe chocolate.
Yep.
Yeah.
2 guesses for chocolate. You're right. It's chocolate, right? So you're able to take this chocolate because it goes from that solid at cold temperatures to liquid at warm temperatures and then back to solid, right? So that's how these 3D printers work. They are able to go from liquid to solid for the most part. So you can see you're actually able to 3D print chocolate if you have all your settings for the printer correct. Oh, what happened? Oh, that was weird. Put that again. So you can see they're able to actually 3D print chocolate, right? So they're actually, so you can see the overhang kind of droops down because chocolate is really, really soft when it gets melted. And it gets a little droopy, but in the right settings and the right materials, you can print really nice things with it. and now I could eat that bottle because it's chocolate, right? It comes out of the machine, you print it. That's just awesome. See, anything that goes from that liquid to solid to liquid state is able to be 3D printed as long as you can get the printer settings right. I want to see what they're printing here.
I wonder what chocolate spaghetti would taste like.
Ooh, I wonder if it would even be spaghetti, because when chocolate gets liquid enough, it doesn't get stringy like plastic does, right? It could get it probably gets drippy, so it'd probably be a big pile of like chocolate instead of like spaghetti like you would think of as the plastics. I could be wrong on that. But
I will try for science.
yeah, try it. Christian is another member of the Makerspace, by the way. He works with me as well. And he actually has done, you've done tests with another student on printing, not chocolate, I don't think, but it was.
We extruded a conductive paste.
Yeah.
So a highly resistive conductive material that was basically like ink.
Mm-hmm.
You could draw like circuits with it and stuff.
Yeah. You can see in this example, it's not necessarily solid to liquid to solid. This is a liquid, but instead of feeding it through like plastic, they're actually using a piston to push out the liquid, and then it solidifies afterwards. So that's another way of 3D printing. Now let's continue. So something else is, what if you combine the two? Now I found this video not too long ago, and I was like, wow, that's awesome. So it takes the idea of machining with 3D printing, right? You are able to build up a structure, and then you use the same machine with a milling bit, like the machining part, and is able to remove material in order to refine it. So this is actually being printed in metal. So this is I think it's a TIG welder, a MIG or a TIG, and it's able to actually deposit it has a metal like wire that goes through and feeds through. And there's super high amount of electricity that's able to vaporize the metal and turn it into well, not vaporize it, but it creates a plasma arc that's able to melt the metal, and it deposits it on this build plate. Now, after it's able to deposit enough metal, you can see how it's not a perfect structure, right? So what they do afterwards is they're able to machine it with a bit to refine the shape, because this doesn't have a small nozzle, right? It has layer heights, but it doesn't have as much control because it's not a small nozzle that it's placing the metal with. It's placing it with arcs, right? So you have to clean it up afterwards, and that's what they're doing here. They're actually taking a milling bit and removing material. You can see that steps as well of each layer the machine is doing automatically. And then with this, they're also able to not just use that rectangular one, they're also able to use a ball-nosed bit. Now, a ball-nosed is it's a rounded cutting head, and they're able to get really smooth surfaces with that. And then in the end product, you get something that looks really nice. So you can see up here how it's smoothing it out. And then that's the before machining with just the metal. And then here's the after smoothing, after all the milling. So you can see this is a way to get not just plastic and wood and that type of stuff. You can, I mean, these are going to be a lot more expensive machines to purchase and maintain, but they're really cool, and they're like something that we're striving towards in terms of 3D printing technology.
Cool. So wait, isn't that like the type that NASA is researching, probably?
I don't know. I've seen a couple things. So I know for sure that one way that they work with metals, especially thin metals, is they do machining on it, but I don't know if they do 3D printing. One thing with 3D printing is there's a lot of heat and then a lot of cold, right? Now that causes a lot of no, what's the word I'm looking for?
Shrinking and expanding.
Warping, but not just warping. What's it called when you twist a wire enough and then it eventually breaks?
Tension.
Not tension, but you do it to a blade too. If you,
Torque.
Oh, fatigue.
Fatigue. It's material fatigue. But there's another word for it. I can't think of the word for it. It's when
maybe.
It's when you take a knife and you heat it up real hot and then dump it in oil to quench it. And it makes it really, really hard. I can't remember what the name of that word is.
I mean, there's cold, I think it's called cold hardening. Something like that.
Yeah, hardening. Thank you. Metal hardening. I don't know why I couldn't think of that. But what happens is it will cause this metal to not act like the original metal, because what happens is after it goes through that heating process and then rapid cooling process, it causes the inside structure of the metal at like an atomic, like really, really small scale to become brittle. And then you have to actually heat it up again slightly and temper it, and then cool it back down again to get rid of that stress. So a problem with that in NASA is that if they wanted to do 3D printing, they'd have to go through this process in order to cool down the filament. I'm getting on something way off topic, but I'm not sure if NASA is. I know NASA is doing stuff with 3D printing. I don't know if it's metal. I'm not part of NASA, unfortunately. Maybe one day, but I couldn't tell you right now. Sorry. But yeah, some things that they have to challenge with is if they're printing with metal, they have to make sure there's no stress in the metal. It's strong enough for the rockets, and just whatever they need it for. So yeah, so that's the metal 3D printing. Where was I getting to after this? Yeah, so in terms of making files now, so that's all the how to print stuff, how 3D printing works. Now, how do you make files? Now, I don't have many slides on this, but I'm going to explain a lot. So if you don't want to make your own 3D objects, you'd probably be able to go find it online, right? Someone might have made it already. If you want to make a cool hook, you might be able to find one online. There's a cool website called Thingiverse. Now, Thingiverse is an online website made by MakerBot, and people are able to post their 3D objects there. People can download them and then print them if they have their own printers, or even modify those files after they get them. Another place, if you don't want to make the file, or if you want to find other people's files and modify them, or if you want to just make your own files in general, is through a website called Tinkercad. Now, I'm going to get to a video explaining how to use Tinkercad in a second. But
yeah,
Tinkercad,
I've seen that before.
Right. So Tinkercad is a really simple website made by Autodesk, and you're able to 3D print. You're able to 3D model things using defined shapes. But you think, wow, you're using defined shapes. You can only make simple things. You should see some of the things that people have made on there. So Thingiverse has their own website. Tinkercad, actually, anything you make on there, because it's free, is also shared with the public. So anything you make is shared. So these are some models that I saw people that had just made recently. On the left one is actually something I made. And on the right and middle are things that other people have made. On the left, this is actually a wireless phone charger. So you'd actually stick your phone on there, and there's a wireless charger that sits on the back in that circle. In the middle, there's like a house setup that someone made. And on the right, I believe there are ghouls or goblins, if I remember correctly. But I'm able to take these files, download them, and then in Tinkercad, see all the parts individually, not just the entire part, and actually modify every piece that I want to. Now, how do you use Tinkercad, you might ask? So I'm going to show you guys how to use Tinkercad through this video, and then I'm going to show you guys afterward as well. So this person wants to make ice cream, right? So these ice cream cones are like, oh yeah, those are simple, but there's a lot of complex geometry there. But the way to 3D print something is you want to think of it as smaller parts, right? So you take that 3D object and you shrink it into smaller bits. So they took, for instance, they're first starting off with this area here. So you can see this is a cylinder with two rings almost. So that's what they're doing first. So they take that cylinder and they take torus and they shape them just right so they fit together. And then they're able to, I'm going to speed this up actually. Able to modify them together in order to create a 3D object, right? And then they combine them together and that creates a more complex 3D object. And you keep doing this and you're able to get a lot of detail with just a couple parts, right? So you can see in this one, they're actually taking that, cloning it inside of itself, reversing it, and then putting them into each other to get that really cool texture of the cone itself. And then they cut off the edge so that it's flat and then insert it inside and size it just right. So there's a lot of small things that go into 3D modeling. So it takes a while sometimes, but after you get used to it, it's not hard. And then for the snow, they just use spheres, right? For the ice cream, they actually use just spheres and they stack them on top of each other. And then that's, for example, used as a keychain. You can hit that to your keychain just using a loop of some sort. And now change the color. That's up to you. Like I said before with the materials and the 3D printers, you can only print in one color at a time. But yeah, and you can do multiple cones, blah, blah, blah. So yeah, so that's just how to use Tinkercad, super easy. Whoops. So now I'm going to ask you guys, there are two models here. There's a chair and there's a snowman. what are the first things that you would see in terms of those simple objects, right? The spheres, the circles, the cones. What would be the first thing you would look at for the chair? Go ahead, Camden.
Like a cube, and you would have to like distort it so that it would be like rectangular and stuff.
Yep.
Yeah.
Now, is that just one cube, or would you use different shapes as well? Or could you do this with just cubes?
Yeah, technically you could do the chair with just cubes, and you could like distort them to make it look like that. Yeah.
Yeah, you got it. So it's just multiple rectangles, right? That you take a cube, you shape it in whatever size you want, and you're able to just put them together. You just position them just right to create objects. Now that's very similar with the snowman. So what do you think the snowman is made of?
Spheres and maybe like some maybe like 2 cylinders and a cone as well.
Yep, you got it. So the eyes are spheres. The entire body of the snowman is spheres. The hat is 2 cylinders of 2 different shapes and 2 different heights. And then the nose is just a cone. So 3D modeling isn't actually that hard when you think about it. However, when you think of something, now I don't have it open, so let me open it up for you. So that's the end of the presentation anyways. But let me open up the 3D model. I'm going to show you guys that 3D model of the phone one I made. I can see all these models I've worked on in the past. You can see this is the wireless phone charger I made. So there's a lot of 3D parts that I put into this. Now, a cool thing about Tinkercad is you're not limited to just these shapes that are here on the right side. What you're able to do is actually combine them in different ways. So for example, if I have a cube here, right, and I want to have a sphere, if I take a corner and remove like a sphere shape out of it, you can actually take a sphere, turn it into a hole. And now what you do is position these just right. I'm just going to do them like willy-nilly. I don't actually care. This is just an example, right? And then if I combine them using this, right, group, what happens is that sphere shape is actually taken out of the cube. So you can do this to create shapes that you actually use as holes again afterwards, right? So now I have an inside radius of a circle that I can use to corner something, for example. Now if I have a cube and I want to do this again, whoops, let's group those, right? And I'll rotate this in just the right way. And we'll rotate it this way. And I'll put this like that and like this, just somewhat like that. And now we turn this into a hole, right? And move it down a little bit more and group these. You can see how you're actually able to take out a sphere of something, but only a section of that sphere, right? So using this is a really complex way, and then combining that and doing that many times gets you something like this, right? So what happens is, actually, I have it next to me. Let me show you guys. All right, so this is my phone charger. This is my phone stand. And what happens is this wireless charger has a plug that comes out of this end, and that will come out of this edge right here and then go back to where the plug is. Now my phone, there's actually a lip here. You can see that right there. And my phone with the case just sits inside of that and leans up against the middle of the phone charger. So the way I got that is I got calipers, I did a ton of measurements, and I was like, okay, here's what I want to do. I want to make it slide. I want to make it angled a little bit. So I made this whole thing angled, and I made a little chair. However, let's see what this looks like if I were to ungroup this, right? So let's ungroup once. And now you can see, okay, this is looking simpler, right? So we got a not a cylinder, but like a hollow cylinder. You can think of it as a pipe. And I just removed the top off the section off the top, right? So that makes it simple. These are just rectangles, so that makes it easier to see. The bottom down here is just a rectangle almost, but except it has these corners here. And then these were removed, these round parts were removed by these. So these are also just, like I said before, the circles and the spheres. This is similar. It's just a cylinder and a square or a rectangle. And this piece here if I ungroup that, very similar thing. I just have a cylinder that was actually stretched out to make that round. And then you can see if I keep ungrouping things, let's just keep hitting ungroup. All right, so there we go. That's how I made the hollow cylinder. All right, let me just group just those back together. There we go. So now you can see all the different geometries that have come together to make this bottom section. Right, so I have a rectangle here, I have a triangle here, I have a rectangle here just to fill in this little gap here, another rectangle, and they're just angled and placed all just in the right position just so that they all fit together. So yeah, so you can make very complex things just by combining these simple shapes. It might be hard to wrap your head around at first, but after a while, it's not that hard. And yeah, you end up with something nice like this. Now let's go to Thingiverse and see what they have online. So,
Wait, excuse me?
Sure.
Before you switch to, can you go back to Tinkercad? There actually are two different views. If you click on the Lego brick right there, it actually shows the model and like shows you how to build it with Lego bricks.
Which button?
Oh,
this one here.
Yeah, up on the top. Yep, there.
I've never clicked that before. Oh, that's cool. Oh, it's so small though that
Oh, that's
it actually
awesome.
I didn't know that worked. Yeah.
There's also a more detailed one. That's the least detailed one. Also, near the top, like
yeah,
the
I can see.
different
Yep.
steps.
Oh, that's cool.
Yeah.
Oh, it's kind of funny with the really thin parts that I have in here.
Yeah.
Let's try something a little bit. Actually, hold on. Let's try something that I have that's a little bit thicker. I believe I have some thicker models. Let's see. So I'm curious. Let's try the snowman that I made for the PowerPoint. So you can see the cones, the spheres. Now, if I wanted to flatten this bottom for just a quick tangent, this wouldn't stand up by itself, right? So I'd actually take a rectangle, flatten it down a little bit, and it's a whole setting. And then I combine those two. Combine, there we go. And now it's flat and it's still on the table. Sorry, quick tangent. Okay, so let's go back to where it was and let's try the brick because now I'm curious. I want to see what it looks like. So this is the simple one. Yeah, that looks like a snowman. Let's go to the detailed one. Okay. That's a little better.
Use that for Minecraft, John.
Oh yeah, absolutely.
Yeah, there's also, speaking of that, there's also on the pickaxe icon there.
Oh
yeah.
no, there actually is a Minecraft. Oh, that's voxel. That's not Minecraft, but yeah, that's fun. Actually, no, it says ice. What? Oh, that's cool.
Yeah, you also can like change it to the detail.
That's funny. You can see I have Minecraft down here. I play a lot of Minecraft. Oh my goodness, that's cool. Let me see what the detailed one looks like. Oh, now that looks good. Let's try, do I have anything that's multicolored? I don't think I do. But what we can do is, like I said, anything that you make on Tinkercad is open to everyone, right? So if I go to, let me see, where was it? If I go to Tinkercad and then I go to gallery, there it is. Now you can see all the things that people have made and posted, right? So let's see, ooh, DeLorean, of course. Oh, no derivatives, dang. I can download it, but I can't tinker it. Let's see, let's find something we can tinker. Oh, the new Ingenuity helicopter. Oh. I wonder if I was wrong in saying that you can, no, you can copy and tinker this, so maybe it's just the permissions per person. There we go. So now I've stolen their model, right? There we go. You can see how much detail they've actually put into this. Ooh, that's laggy. That's a lot of parts. Here we go. Let's see what that looks like. It's gone. Maybe it's just, it's thinking. There's a lot of parts.
Yeah, it takes a long time to load with those
There
ones.
it goes. Oh, that's cool. That's awesome. Let's see the Lego one real quick. Now I'm messing around. Now I'm not even doing the power. Well, then again, we're done actually. It's been 50 minutes and we've gone over the entire PowerPoint and everything that I wanted to cover. Also the different blocks correspond to the, yeah, I've noticed that too, especially even with the, let's go back to the Minecraft one. It actually chooses the blocks based on the color, which is awesome. So for example, it says TNT. Oh, you can actually change, you can change the colors here. Oh, wow. for the specific parts. That's cool. Is there any questions on the PowerPoint or even on this?
I have a quick question.
Sure.
Can we print these Lego or Minecraft models or whatever?
Let's see if I can export them as
Can
those
you export them
blocky
as
files.
STL file?
Oh, it exports them as schematic. Schematics are Minecraft files. I don't know. Can I turn schematic?
We actually did that at the Makerspace, remember? We turned schematic files into STLs and we printed them for people. So not directly, but you could via a third party. I know Blender has a schematic plugin you can get, and you can load them in and export them.
I wonder. Let me try something. I want to try something. Let's see. If I download this onto my desktop, all right, this is schematic. And if I open, this should be able to do it. One moment. Let's try open other world. And this is for like 1.16. I wonder if this works with 1.16 stuff.
Also, on the Tinkercad, if in the thing with the arrow on the basic shapes, if you click on it, then it turns out that there are like also these tons of different things.
Oh yeah, there's tons of things that you can look for.
So as the skeleton.
Yeah, if you guys want to, I would absolutely recommend going in here and modeling your own things and just messing around with it. It's so much fun. But I'm curious. I want to see that schematic. Can I open this world?
Don't be fooled by how "quote unquote" childish it looks.
Pretty
much everybody in the 3D printing community uses Tinkercad because it's so robust. Everybody uses it, so
it's so simple that anyone can use it, but yet it has enough features where you can do a lot of complex things with it. One thing that it can't really do is sculpt molding. For example, you can actually take a sphere and like indent a section of it to have like a nub. That's something that's not as easy to do with Tinkercad. You'd have to actually build that up part by part. Yeah. So there we go. Let's see. Let's see here. Can I import that thing? I wonder if I can import schematics. Maybe I can't. Let's try it. No, it doesn't let me. I might have some old 1.12 worlds that I can load a schematic into though. Do I have MC Edit still? One moment. No, not done Minecraft. I want to go to Minecraft. Oops. Where'd that folder open? Oh, there's Minecraft, MC Edit. No, I got rid of it because it's outdated. Darn.
Well, John figures that out. I'd just like to mention that don't think that 3D printing is like super inaccessible. You can get some starter machines for $150. So maybe for Christmas or something, maybe instead of getting a PS5 or a console, get a 3D printer. They're very accessible, and there's like thousands of people around everywhere to help you out. So 3D printing is accessible, and it's definitely for everybody. So I would encourage everybody to get one at one point. I have two. I'm a bit of an addict, but get 3D printers. They're cool, and they're not as expensive as you think they are. So look around.
Not supported schematic. Wonder if I can find just a converter online.
Yeah,
well, we're getting very off topic, but whatever.
Ender one, like, right.
Go ahead.
There was this one thing that you showed us in the slideshow where it was like before it was ready to print. What's that application there called?
This one. Let me scroll a bit.
Yeah, that.
There, this one.
Forward. Yes, that one.
Cura.
So this is Cura. So I'll actually open that. I'll show you guys.
Yeah.
This is Cura. So Cura is a free software that you can use, and you can import. So you can create a profile for your printer, and then after that, you can just import models, and you're able to print anything. I'll actually even load up the same model that I showed in the slideshow, the spaceship. Let me go find that picture. I believe I put it in here. There it is.
Also, thanks, because that was one thing that I was really wondering about.
Yeah, so like I said, that's just software. There are different softwares that you can use, but I use Cura. We here at the Makerspace use Cura. All right, so this is the spaceship that I have. It's from a game called Elite Dangerous, right? So you can see there's a lot of fine detail in here, blah, blah, blah. However, when you print at really small scales, you don't get the super fine detail. For example, these grids are really hard to see, especially with the nozzle, depending on the size, but I can even show you that. So here we go. We'll load it in. I have my profile set up. So I've gone through a lot of these settings. I'll just open it up and scroll through them kind of real quick. So you can see there's these different tabs, right? So quality is for how high the layer is. The shell is the outside layer. So if I go to preview, shell is the outside layer of the printer, of the print. And then we have infill, which is, like I said, the patterns on the inside. So you can see the inside here. And I said I would show that, so thank you for reminding me, actually. I'd show you a couple different infill patterns. We also have materials, so you can change the temperature and the actual bed that is printing on the temperature, speeds and how fast the printer moves, traveling, retracting the filament every time it changes so that it stops it from stringing, cooling, the fans, the support. So the support is like this stuff in blue, the part that lets you print in midair. You can change those settings. You can change build plate adhesion. I have that set to none right now. Mesh fixes, those are if your STL file is broken. Special modes, experimental, blah, blah. But yeah, in terms of the support, I will show you guys. So let me make this bigger, and I will show you guys. Let me show everything first. So you see, this is the model. And remember, in here is where the detail was. Let me hide the helpers. And you can see how those grids are non-visible, right? Now, if I were to take this model and make it a lot bigger, if I print it too big, it won't actually slice it because it's too big for the printer head. But if I let this slice now, give it a moment, because now it's a lot bigger, so it has to do a lot more calculations for the coordinates. Give it just a moment. Why is someone calling my house? Give me a moment. Cool. Okay, so this is the model a lot bigger. You can see that stepping effect is not as much because it's so much bigger. You can see in here now the detail is actually being shown of those grids, something really small. But you're still going to get that stepping effect like the mountains, right? I actually have it printed. Here we go. Here's what it looks like when it's printed, when it's printed upright like this. So it's able to actually, I don't know if my camera is going to cut it out, but let's see here. Let's focus on the print. There we go. So you can see how it's really, really smooth. Now, here's an example of a print that was done with it printing this way. So you can see if I focus onto this guy now, you can actually see the stepping effect. My camera keeps cutting out of the layers. So yeah, printing orientation is important. That layer height is important. And now support. I'm going to show you guys the infill if I rotate this. So this is really fun to watch sometimes. So I'm going to rotate this upwards. It might be too tall. Nope, we're good. I'm going to make it a little bit smaller just so it slices a little quicker. All right. Let me minimize all these tabs. All that slices. Should probably go even smaller because I'm going to change it a couple times. Actually, I may use a different, bigger model. Let's see, what models do I have? I think I have a cube in here. Calibration 10 by 10. Cube. There we go. And then we'll make that a little bigger. So Cura in here has a couple tools, right? So I have this move tool that allows me to move it around the build plate. It has a scale tool that allows me to change the size of it slightly, rotate, where I can rotate it. And then there's other tools, I believe, I can't remember what this one is. It allows you, I believe, to rotate the part based on what direction you want to have it face. These are for meshing, like if I multiply this and put it into itself, the actual overlap stuff. And then this one, I actually don't know. We can see here now. So we have the cube. If I were to go through it and look at it, you can see the pattern. This is called gyroid. And this is, I think, 20% infill. Yep, this is 20% infill. Oh, no, sorry, not gyroid. This is cubic. You can see how it's actually triangles that actually go upward. So if I pull it this way, you can see how that pattern changes as it comes up. Now, my favorite one, like I said before, was gyroid. Now, cubic is really strong because it has those straight lines going in multiple directions, instead of just those grid-like ones that were before in the slideshow where it's just up and down, it's repeated. So you can see here's what it looks like if gyroid. So this is really fun to watch. Right. So if I go up from the bottom, you can see how it's actually printing these weird wiggly lines that then intersect and hit each other. Now, this isn't as strong as cubic because it's all bendy, right? There's no straight lines. It tends to be in mechanics. I think, Austin, you can confirm or deny this, that a straight line when compressed this way is the strongest versus if you had an arch and you wanted to press it from this way. Normally you want something straight.
Mm-hmm. Yeah, because if you have anything curved, when you push it, it creates like a bending moment, so it'll go upwards.
Yep. So yeah, so straight lines are fun, but these are the funnest to watch when they print. Now, then again, they also print a lot slower. This cube alone, which is only, how big is this? This is only 2.7 centimeters, 2.7 centimeters to inches is about an inch. Yeah, about an inch. So this is an inch by inch by inch cube, right? And it takes an hour, right? Because what happens is it has to draw each of those lines layer by layer. So something like this takes a really long time.
As a converse, if you print something with no infill, like John was saying, it takes a lot quicker. So let me give you an example. Does anybody recognize this? Anybody? It's Bugs Bunny. This thing is completely hollow. You can kind of hear it. Completely hollow. This thing took like 4 hours and it's massive. And so, yeah, you can print things hollow and print it very, very quickly. But if I drop this, it would shatter into a million pieces. So it's a bit of a trade-off. But if you wanted to put something on your desk or something, print it hollow. It's not going to be thrown around or anything. But if you wanted to print it more solid, like this, see, this has a pretty solid infill pattern on it. This is a lot stronger, but it takes more time.
I got a question for you, specifically for Bugs Bunny. Do you remember how thick you made it, or is it just a single layer thick, like the vase?
It's a single wall.
It's a single wall. So, like I said before, when we were looking at Einstein, the actual wall thickness on the outside was really thick, and that's done over here. So if I were to change this cube, so for instance, this is 0 infill, right? Because there's no pattern on the inside to support it. However, you can see here, there's 3 lines on the outside. Wall line count is set to 2, but based on the thickness, it goes to a certain amount. If I were to set this to like 10 or something, just something extreme, you can see how much thicker the wall gets, right? And there's no reason at this point, unless it's super big, you don't need an infill pattern because it's so strong in the outside. There's no need for support, especially if it's something that's just like sitting around on your desk. But yeah, if I set it to 1, for example, like Bugs Bunny, or there's a special mode called vase mode in printers, you can see how it's just a single layer thick, or 1 layer on each side, just to get it to the right thickness of the model. I think I will get into vase mode, actually. I believe it's in special mode or in experimental. Or is it called? I think it's called single.
Like spiral. They call it like spiral contours, so it just goes up
something like that.
Like
there we go. Special mode. So instead of doing layer by layer, it actually draws like circles, like a helix almost, and it keeps going up. But it's not necessarily a helix. It actually follows the shape. You can see how it actually will keep going up almost. and it will actually do that for each layer. And you can see how it's actually a single layer thick now versus trying to get the one wall thickness before. If I show something a little bit more complex, let's do something like, I have some Ender 3 parts in here. Let's see. I don't have anything good, I don't think. Well, let's do something from, let's do a spaceship again. Let's do, where's the Mamba? Or Anaconda. Anaconda, there we go. All right, so here's the Anaconda. Now this is gonna be really hard to print, so I'm gonna print it upright. Oop, not that way, I wanna print it this way. There we go. So this will also minimize the support structure underneath because you only have to support a smaller surface area this way. But let's see what it looks like with vase mode. Okay, that's not that bad. So what vase mode does is, oh, that's not good. So what it does is it tries to print just the very, very outside of the print and nothing else. Versus if I turn that off, it's going to take a minute to print, but it's actually going to give it some thickness. Or actually, let me reset my profile. Oh, it's freezing because it's thinking. There we go. Let's discard those changes. Let's go back to my default profile settings, and it should look pretty good. It should actually look like the Anaconda versus having holes on the top from looking at top down. But vase mode is really good for vases, obviously, or something that's tall and non-super complex. I don't know why the bottom of that isn't printing. That's weird. Oh, wait, it's this. There we go. Let me change the line type so you can see it. There we go. So you can see how on the top now it's actually filled in. On the inside, there's actually a support structure, and then there's thickness to the wall. And yeah, this would last you, you know, even if you like threw it around, it would probably last you a while. Just with these settings, because it's thick enough on the inside that it won't shatter. I think we've gotten off topic enough, and I think I've held you guys up enough. Does anyone have any last questions? And I think we'll call it there.
Great.
Cool.
Thanks,
guys.
Wait,
Thank you.
I have one last question.
Sure.
So, can we, like, is it possible for us to copyright something we've created with our 3D printers by using a program like Tinkercad?
You would have to have access to the 3D file. So if you wanted to model something and recreate it, it's technically inspired by. I don't know the laws behind that, but Christian, you wanted to say something?
I believe if you create anything, it would be your intellectual property. So Tinkercad, I don't think they claim a right to your intellectual property if you use their platform. So if you made something on Tinkercad, it's yours. But I think somewhere in the terms of service, they may say that by using this website, you're granting other users access to your intellectual property. But if you were to use your own program, such as Blender or Cinema 4D or anything like that, you could claim copyright. You'll see that when you download, I don't know if any of you have downloaded models or mods for games, but a lot of times they will have a terms of use or like a license. But yeah, if you make something on your computer, most of the time it's your intellectual property.
Yeah. If you wanted to steal a file, you could technically take it and use it. You wouldn't have the rights to own it, right? So if someone's selling a 3D file, for example, you couldn't then, it would be illegal to then go out and try and sell it yourself if you just take their file, right? So if you pay them by the actual 3D model itself and then resell it as yours, that would be illegal. Yeah, I think that's it, guys.
Cool. So wait, are there any like summer camps or online forums for like
I'm sure there are. I don't know of any that are around the community. You'd have to check with the community, right? So a lot of communities actually have public makerspaces where they might not do specifically 3D printing, but they might do woodworking, metalworking, those types of shops, but they might have 3D printers.
A lot
I
of
would look it up.
libraries have 3D printers. Like lots of
Yeah, I
more
was gonna say-
libraries are having them now. So
I was going to say,
Check
yeah,
with the
libraries or
library.
schools sometimes have them. Yep. Yeah, I think that's it then. I want to thank everyone for joining us. Yeah, if you want to get something 3D printed, you might even be able to contact the makerspace. You'd have to work that out. So the way we do that is we only do it for students at UMass Boston. However, if you really need something printed, go to, I think it's makerspace.umb.edu, and let me double check.
So
Makerspace.umb.edu. I'll put that in the chat if anyone's interested. And if you want to request a print, first get in contact with us, because you're not UMass Boston students, most of you. So get in contact with us first, and then we'll get approval, and then we'll see if we can get it out to you. So yeah,
great.
Thank you.
Also, I forgot what the name of that website where everyone like shared their 3D prints.
Thingiverse.
Oh, Thingiverse.
think universe, but thing.
Okay. great.
Thingiverse. Yeah.
Thank you.
I'll put them in chat too. There we go. All right, guys. Thank you for joining. I hope you have a good time. There's a lot of other community events going on at the Cambridge Science Festival. So if you're like something like this, or you want to see more science stuff, look on the Cambridge Science Festival website and see if there's anything else that's cool. Well, that's it for now then. I hope you guys have a good weekend. Take care.
Thank you,
Okay.
Gianluca. That's
Have
great.
a nice day. Bye.
Bye.
Thank you.
Goodbye.
Goodbye.